I hope it's working. Microphone, sound check. I don't know, the little circle's winding up for me. I think it's working. We're good to go. Hello, YouTube, Twitch, Twitter, LinkedIn. Anyone else who might be watching? Don't know how you're watching, but if you're not on one of those 4 platforms, otherwise. Today we're going to be doing something I haven't done in a little while. Used to do some blockchain engineering broadcasts once upon a time. It's been a few months since I've done one. I had to go to the bathroom, sorry. But I'm back now. We're going to do one. Today we're going to be building a transaction generator utility. Now that sounds kind of lame, but it is like super necessary for testing purposes in particular. Okay, so when you have like an actual blockchain, one that's running up in the wild, processing transactions and whatnot, those are coming from a user. Bitcoin has a gazillion transactions going on all the time. And because of that, you can, because it's using real world data, you know how the network performs. You don't have to guess. It's like, it is what it is. However it's behaving right now under current user throughput, that is, that's how the network's going to behave. But if you're still in the engineering and development phases, early phases of a blockchain, if you're creating something new, well, you don't really have a whole bunch of transactions running through your system to know how it's going to behave. Now, like Topple's no exception. And in fact, we really need to know how our network will behave with a bunch of actual user transactions in the mix. That's really tough to do without users using our network. So we have to fake it in order to simulate it. But in order to simulate it, those transactions need to be valid and correct. Otherwise, we're not really testing anything. We're, I don't know, just making data, making a utility that does a thing. It needs to do a useful thing, though. So we need to generate transactions. They need to be valid. And we need to be able to use those transactions and see how our network behaves. That's one reason. I mean, there are a few other reasons. But in particular for tomorrow's broadcast, a little sneak peek, we plan to really push a Raspberry Pi to its limits. So in order to do that, we need to have a utility that can, I don't know, push it to its limits. So that's part of what we're going to do today. So problem statement, you need transactions in order to test a blockchain. So our objective here today is to create a new utility that generates transactions. In particular, they need to be valid, and they need to be able to be used on a blockchain. Our blockchain, to be precise. Okay, so again, this is engineering focused. I'll be doing, I don't know, like 95% code today, maybe a little bit of diagramming. So if you're more of a developer or engineer mindset and you're interested in this workflow, then stay tuned. Otherwise, if you're kind of just curious how developers work, you also feel free to stay tuned. Okay, let's hop into the code. So I'm here in our Bifrost repository. I've created a branch called Tetra TX Gen. So Tetra Transaction Generator. Might rename it, just want something for now. So first step, I need to build a new utility. I don't like to just add utilities into existing utilities. Like it just kind of bloats the software up a bit. So I'd rather just create a new module. So we'll open up our build.spt. Okay, so here in our build SBT, we got a whole bunch of modules. And we're gonna keep growing the list. So let's copy paste I don't know, one of these. Networking would be fun. And I'll paste it. And I'm going to rename this. So it's going to be, I don't know, it would be a fun name. Well, how about transaction generator? And name the file transaction dash generator, and same thing with the module name. Now, only going to care about Scala 213. I don't really feel like supporting 212. It's kind of annoying to deal with. We do for some libraries, but not for all of them. Okay, probably don't need a lot of these things here. I'm going to delete algebras. We don't need consensus. Probably don't need common interpreters. We'll see. Don't need cats akka. Plan on using just cats and fs2 instead of akka. Going to delete event tree because I don't think I need that. Going to delete ledger. And then we need to add some dependencies. So I'm just going to transaction generator. So it doesn't exist yet. So let's go and create that. Just create it right below here. And so these are our library dependencies. So, like Maven dependencies that we depend on. So we've got some test dependencies. Yep, that's good. We're going to use cat's effect. But we're not going to use akka, but we are going to use fs2. So dependencies.fs2 core. And again, because we're not going to use akka this time, we don't need fleem either. This is using Scala test for the test dependencies. I want to use munit test. So change that. Okay, transaction generator. I don't think I'm not going to use mocking at the moment, but I could incorporate. Yeah, I'll add it in the munit Scala mock. Help me out, IntelliJ. I forgot what I called it. This thing, just a little SBT module that allows you to use Scala mock with munit, which you can't currently do. Okay. That's probably good for now. Okay, so let me talk through some of these here. So why do I need models? Well, I need models because I need access to the transaction model. Talk about this a little bit more in a second. I need access to this, and it's located in the models library, or module, I should say. So I'll bring that in. Type classes. I'm going to need access to, well, there are going to be like some helper functions that exist on top of models that I'll need, so I'll bring those in. Crypto, because I need to be able to sign transactions. Byte codecs, because I need to be able to, byte codecs and tetrabyte codecs because I need to be able to come up with the bytes to sign. So again, going back to the crypto. And finally, munit Scala mock, just a utility that, yeah, I already said that. Okay, so that's our transaction generator. Go ahead and load this up. SBT, do your thing, I believe. Okay. And so SBT is just creating, well, the module for me, and that's going to create a directory that I can use. Eventually. I guess while it's doing that, let me talk about strategy here, or I guess, transactions. Let's look at this one right here. So I just have a little quick diagram of it's a lightweight transaction. There's more to a transaction than this, but a transaction is the way you modify data in a blockchain. Or I should say consume data and create new data. That's another way to think of it. So these yellow circles here are the inputs to a transaction, and these are what consume the green pyramids, or whatever these are, of a previous transaction. Okay, so yellow circle is a transaction input. Green thingy is a transaction output. So when you construct a transaction, you need to define the inputs, which means you need to define which outputs you want to consume. Then you also need to define which outputs you want to create in your transaction. and that kind of just builds from there. So initially, at the beginning of the blockchain, there is there's just a block. The Big Bang block has a transaction, could be multiple transactions. But for now, let's just pretend one transaction, and it only produces outputs. So once you have an initial set of outputs, these can now be consumed by new transactions that get broadcast into the network. So this transaction here just decided to consume both of the outputs of this previous transaction and then created a new output that can be consumed later. And then a new transaction came in where it consumes this single output of the previous transaction, and then it creates two new outputs. Then from there, we have a transaction up here, consumed one of those outputs from the previous transaction, and created two new ones. And then a different transaction down here consumed the other output of the previous transaction. So this is like in general, like the transaction graph is what it's called. It gets way more complicated from here, but this is just like a simplified one. So in the real world blockchains, these are users that are creating these transactions, and this user here decided to spend this transaction right here, or this transaction output, and then a different user perhaps decided to spend the other. And so it's users that are responsible for creating transactions and generating all of the data and everything that needs to be validated in the system. So in order to make sure that our system behaves the way that it should in the absence of many users, we need to be able to generate these transactions. And so that's what we're doing today in our little utility. We're going to pretend to be users. Okay. Now, SBT has finished, so go ahead and we have our new directory here. And I'll create a subdirectory source /main /scala/code/topple/ I can already see an issue in my build SBT. I'll fix that in a second. Code topple transaction generator. Ugh, that's ugly. Don't care. Doing it anyway. That's our new directory, and then I'm gonna also fix this real quick. Transaction generator. It's not super important. It's just for build info, but might as well make it correct. Okay. Now, I've created a new package code topple transaction generator. I like with the Tetra code base in Bifrost, I have adopted an algebraic style for coding. So you'll often see like a module like this contain, well, at least 3 directories. Well, maybe at least 2. But the first one we'll start with is algebras. And an algebra is like an interface in other languages like Java. And it just defines a few abstract methods that need to be implemented by something called an interpreter. And an interpreter is like an implementation in another language, or like a concrete class. Okay, so we need to create an algebra. I'm going to call it the transaction generator. So it's I define it as a trait, and I'm going to define a type parameter f, but it's a special one. This type parameter f also needs to have its own subtype parameter that, I mean, we don't care what the subtype is. It just needs, f needs to be able to handle having a single type parameter. This is called a type constructor. So if you're unfamiliar, something like, option int would follow this pattern. Okay, so in this case, option is our f type. And then, int is like just the underscore here. Because this could be option int or string or whatever. Option doesn't really care, just has a single type parameter. Okay. This is typical in the tagless final approach. Is like kind of a way of implementing the algebraic design pattern. It also does a couple other things, but it's very typical in this pattern. Okay, so there's going to be this f underscore. I'm going to keep going for now. I'm going to define another type parameter in a second. Anyway, this is going to have a single method, generate transactions. Going to return an f, and then so this is where I need to do something in here. Having it return an f, this is just typical in the tagless final style. So like every single method that I would define here all returns an f and then some other type inside. So what's that some other type in this case? Well, I need to generate ideally an infinite stream of transactions. Okay, I don't want to just generate like a list of transaction because maybe I want this to be able to generate millions and millions of transactions and like run forever essentially. So a concrete list, it's probably not what we want. Then again, we don't want to impose that it not be a list. So the algebra for now, I'm just going to define a second type parameter, g. It's going to look very much like our f, but this time it's just going to represent this collection type of transactions. So swap that in. So it's now going to return whatever this f is, but then the subtype is going to be whatever this like collection type is, g, of transactions. Okay. So we have our algebra. Going to create a new package here, interpreters. If I could spell it, interpreters, yep. And I'm going to implement this. And so how am I going to interpret this? Well, I'm going to interpret it using FS2. So FS2 is functional streams for Scala. It's part of the type level ecosystem, so it plays very nicely with, like cats and cats effect and everything like that. And so yeah, it's a streaming library. So that's how I'll interpret it. So I'm going to interpret it as like FS2 transaction generator. Now the interpreters usually are defined inside of objects with a sort of like an apply function, but it's intentionally not called apply, but we call it def make. So we're going to make something. Going to have parameters of some sort. But it's going to return in, whoops. It's going to return an F transaction generator. So I'll implement my algebra, and so it doesn't have an F, so we'll give it one of those. F type parameter. Okay, so transaction generator requires two other type parameters, so we'll plug in F for this first one. And then for G, this is where things get a little funny. Not funny, but this is where I'm going to pin down the the type for G. So because I'm implementing with FS2, I'm going to specify stream. It's going to collide with the Scala one, so I'll go ahead and import fs2 dot underscore. So it's going to be a stream, and so stream again requires this f, so I'll plug that in. And then for the second one, well, this is where it gets funny. We can't just like say, transaction or whatever, because it needs to be an underscore. So this is where we use asterisk, which is from one of these plugins. It's not defined in here, is it? It's going to be in the build SBT. I don't feel like looking for it. There's a plugin that we use, and I don't remember the name of it. I'm super helpful, aren't I? You're welcome, everyone. But it allows you to shorthand something like Oh man, this isn't even gonna be fun. And never mind, I'm not gonna bother. It allows you to shorthand a syntax. It's like this is so much easier to write than whatever I was about to just try to do. That like this does what I was about to just do. It allows you to specify that this is the type hole that we're interested in. Um, because again, our transaction generator is expecting a type parameter with a single type hole here, but stream has two of them. So it can't just do that because stream has two things need to be plugged in. So and down one of them, and then I make the other one abstract. It's a type lambda, I think is what it's called. Anyway, I'm rambling. 20 minutes in already. I haven't even done anything. Let me get going here. Uh, okay, so I'm just going to do sync dot delay and do that for now. So again, we'll import. I don't want to import from kernel. Just import that. Okay, so it doesn't have a sync, so let's give it one. And we need to, at some point, return a new transaction generator. F stream F. Oh my goodness, so much typing. Fill that in for me. Okay, and now generate transactions. And for now, I'm going to, let's just stub in so that it returns an empty stream of transactions. So sync dot delay again, stream dot empty. Okay, so we have an interpreter. It's a really useless one because it's just returning an empty stream, but we got the basic scaffolding in place. It's enough scaffolding that we can go and write a unit test. So we'll create a subdirectory under source called test, and then Scala, then code, topple, transaction generator, and then interpreters. And we're going to create fs2 transaction generator spec. Okay. Again, because we're using munit, we're going to use cat's effect suite. And I always do this at the start. I like typing F instead of IO. I don't know why. Maybe because it's one less letter. Okay. Um, reduce and empty stream. That's going to be our test here. It's obviously super rudimentary, but whatever. Okay, so our tests here, they need to return the IO type. They don't have to, but I'm going to. So to get started, we need to define our thing that we're testing. So under test, fs2 transaction generator dot make. That's an F for a type there. Okay. And now let's generate some transaction. Well, let's generate our transaction stream. So under test.generate transactions, and this should just return a stream of transaction. Cool. And now we need to actually consume that stream. So stream dot compile dot to list. Okay, and now we can run just a quick assertion. Transactions dot is empty. Go ahead and run this. So if anyone has any questions about what I'm doing or how I'm doing it or why I'm doing it, please feel free to leave a question in the chat. I might even answer it if you're lucky, if you're nice. Look at that, it passed with flying colors. Okay, so that's obviously a very useful list of transactions given that it's empty. So we need to do something with it. So Let me hop back to this thing real quick. How do we generate a stream of transactions when all we have is this? Okay, so this is that Big Bang transaction that contains some outputs on it that can be spent, by people later down the road. For testnet scenarios, we're going to assume that whatever output or outputs are on this Big Bang transaction have a proposition that allows them to be freely spent by anyone. In other words, it's going to be a height lock of 0, which means that as long as the height of the chain is greater than or equal to 0, uh, the output can be spent. So any block after the Big Bang block will have that height greater than 0. Actually, even the Big Bang block itself would have that. So that means that anyone can spend it. Now our goal here is to generate the rest of this stuff using just this one Big Bang transaction. Okay, so I'm going to call this, let's just call it the seed transaction, because maybe it's not a Big Bang transaction. Maybe we're launching this transaction generator from the middle of the chain. For example, maybe we're launching a generator that starts from here. So I'm going to call it a seed transaction. This is just the transaction that contains things that are freely spendable. Let's also define what I mean by freely spendable. Let me update my import from models. Okay, so I said that there was a height lock proposition. So let me go and define a height lock 0 proposition equals propositions dot contextual, because it's based on the context of the chain, dot height lock. And I'm going to say height lock of 0. Okay, so this is our proposition. And then there's also going to be an address associated with it that I'll need in a little bit. So let me go ahead and do that. So val height lock 0 spending address. This will be a spending address equals height lock 0 proposition dot spending address. Now you'll see it's coming up in red because this thing does not exist on height lock. Nothing exists here. It's just a basic case class, just a basic structure. So that's where that whole type classes thing that I mentioned, where that comes into play, where we needed this thing. So I'm going to import co.tople.typeclasses.implicits.underscore. And voila, we get this method called spending address. And spending address right now, well, it's a type class, and currently we derive it from anything for which there's a contains evidence type class instance. And so we've got several implementations of it. I think that it's just pulling from the immutable codec. I don't remember. Oh wait, no, I was looking for a proposition height lock. This is where it's pulling from. So this ultimately gets used as the spending address of our height lock proposition. Okay. So that's what I'm going to assume is in here in this seed transaction is an output or some outputs that contain this as the proposition. So let me first start by extracting that, and I'm also going to turn this into a for comprehension. I'm just going to yield a. Oh no, let me move this here. Okay, so first thing that I need to do is I need to extract the initial set of spendable outputs from the seed transaction. So let me back up a step. Approach here. I need to generate something. Well, so starting from here, I need to generate another transaction that spends at least one of these outputs and then creates its own new set of outputs. So in order to construct a transaction, I need to know what outputs are still available to be spent. Um, and I need to know the propositions associated with the addresses that I want to spend. And then I will also need like secret keys for like future outputs if I want to do that. In other words, what I'm describing is like a rudimentary wallet. That's going to be a term used differently in the SDK that our SDK team is working on. But for now, I'm just going to kind of abuse the name a little bit. I'm going to create a model called wallet. I'm going to just define a few things in there. So again, this isn't how real world users would use it. I just need something that looks kind of like a wallet for now. So it's going to be a case class. Case class is going to contain, let's say, spendable box IDs. This is like, you have your own physical wallet, like that you carry around in your pocket, and you've got like dollar bills in there. So these are the things that you could spend. So spendable box IDs. I'm going to define this as a map from box.id to box. Yeah, box. We'll go with box. So import that from our models. So at the very least, we have this. Then we also, okay, so another thing that's semi-secret, but not really secret, is the association from an address to a proposition. And the reason for that is for post-quantum security, so that you're not revealing verification keys on the chain before you need to, because that could be broken by quantum computers. So we need some way of associating an address with proposition, so we'll store that in like a little memory bank as well. So let's just call it propositions, and it's going to be a map from typed evidence. So a spending address is basically just typed evidence. And then it's going to map to a proposition. Okay, so if you have a proposition, you can always get its typed evidence, but you can't go the other direction. So that's why we need to hold on to this, because it's sort of like secret data. So we have those two things in our wallet. We could also include something like secret keys, but for now I'm not going to do that. We'll keep it simple. We'll just deal with the height lock propositions. Okay, so my plan here is to use FS2 to do like a stateful stream that just emits a new transaction based on the current state of the wallet. So anytime something requests a new transaction from our stream here, we're going to hop into our wallet. We're going to pull out at least one of these spendable box IDs. We're going to construct a transaction that spends it. We're going to create new outputs, and those outputs will be introduced back into our wallet that can be spent in a subsequent transaction. Okay, so let's go ahead and do that. So hopping back into here. So what I was first going to do was like extract the outputs and everything, but like our goal is to create this initial wallet. So it's going to be, I have a cheat sheet. I'm just going to pull it up. I'm sorry, y'all. I'm gonna move this into a separate method. Private def initial wallet. Again, it's going to take that F type parameter. We're going to use sync again. It's going to take a seed transaction, and it's going to return an F wallet. Okay. And I'll implement it in a little bit. Call this wallet and then call initial wallet. Actually, in our seed transaction. Yeah, it's so red arrow here because I didn't import implicits from cats. Okay, so this evaluated the flat map, which we get from flat map, but most of the time you think of it as monad. Okay, so now we have a wallet, and now we need to modify our stream down here. We're going to, instead of returning an empty stream, we're going to unfold from an empty wallet. Well, not an empty wallet, but this initial wallet. Unfold the eval to be precise. Is that f type parameter? Okay, so the state that we're going to like unfold is just our wallet. And then the value type that we're going to produce in our stream, like emit downstream, is a transaction. So our initial value for our unfold is going to be our wallet. And then our function that we're going to invoke on like each time we need to process an element of the stream, the function we'll invoke is to modify the wallet by creating a transaction using it, and then creating a new wallet, and then returning the tuple of those two things. Okay. So I'm going to create another helper method to actually do those last steps. So private def next transaction of, and I'll pass in, again, I need another, like an f underscore parameter. I'll leave it as sync for now. I will need to update it in a second though. Anyway, we need to construct the next transaction using this wallet. We're going to return a tuple, well, inside of an f constructor, tuple containing a transaction. It's like the transaction that we want to emit or broadcast. And then an updated wallet. Again, because our wallet is immutable, it's a case class with an immutable map for these two things. So we can't just like modify it. We need to return a new copy. Okay. Again, I'll just triple question mark this for now. So hopping back into here, our unfold operation is now just calling next transaction of, we'll pass in the wallet. And once that completes, this right now this returns a tuple, but it needs to return an option tuple. And the way that unfold eval works is like if you return none, then that completes the stream. Otherwise, if you return some value, then it continues on. So I have, well, I'm not going to introduce anything too fancy in here. So I'll just map and then I'll map that into some. Okay, I realize I have like a tendency of like being really terse. Let me broaden this back. Make it a little bit more explicit with what's happening here. So our wallet is being passed into next transaction of, and then out comes some tuple of transaction and wallet. The wallet gets pumped back into the unfold operation for the next iteration. Then the transaction gets sent downstream to consumers or whatever's consuming. Okay, so we've got like the basics stubbed out. Just give me 1 second, sorry. Need water. Turns out talking is hard. Okay. So, how do we construct our initial wallet? Let's go ahead and implement this first. Okay, so the sync isn't technically necessary here. I could have just done this with applicative, or I could have just returned a wallet immediately, but whatever, I'll do it this way. So sync.delay. This is, again, it's like using call by name type thing. So instead of immediately evaluating whatever I'm about to type here, it's going to wait until it needs to evaluate it or until it's actually needed. So that's what sync.delay is doing. Okay, and I want to return a wallet. So let me just pop this open here on the right, just so we can see what we need to provide. So we need to provide spendable box IDs and an initial set of propositions that we know about. So the spendable box IDs from here, how do we compute that? Well, we could step through each of the outputs. Real quick, a box ID is a tuple containing a transaction ID and a transaction output index. So a transaction ID and a number, where the number points to the element on that transaction output list. So because I need that index, I'm going to zip with index. Now I'm only going to collect the outputs that I can actually spend. So I'll collect case output index, but only if the output has an address where the spending address is equal to this one up here that I care about. So the height log 0. Okay, so again, we want to just pick the outputs on this Big Bang transaction that have a proposition height log 0. All the other ones we're going to ignore because we presumably can't spend them. It's not even worth collecting them. So if the output spending address is this thing, then we'll keep it. And in particular, we want to, well, here. So the box ID that we care about is going to be, so first item here is the seed transaction ID, seed.id. Then the second thing is the index that we care about. So index.toShort. That does not know that. So I need a couple more imports for some byte codecs to give me the identifiable instances. So .tople.codecs.bytes.implicits. That gives me syntax, and now we need some instances for tetra models. That's in bytes.tetra.instances. Now this should resolve. Yep. Okay. So now we have this ID method on a transaction, which we didn't previously have. And now we have a box ID. So that's the box ID that we're going to spend. Then the box that we care about is going to be, we need to construct this because it's sort of a synthetic type. So a box contains two fields. One is the evidence. So the spending addresses typed evidence, basically one and the same. And then the second thing is the box's value. Okay, so I'll go ahead and construct that. So the evidence is output.address.spending address typed evidence. And the value is output.value. Cool. And finally, we need to return these as a tuple. So box ID and then box. Okay. So this needs to be a map. Right now I have a chain. So let's do toIterable.toMap. Honestly, this could probably be a non-empty map from cats. It would be better because this needs to be non-empty, otherwise we have nothing to spend. But we'll just leave this here for now. Okay, so now we have our map of box IDs that we can spend. So we took them out of this seed transaction. We took any output that has a height lock of 0, and we know that we can just freely spend it. Second thing we need to construct is the propositions. So propositions that we know about, well, it's only one. It's this one. So we'll go ahead and define that. So map from height lock 0 spending address dot typed evidence to our proposition. Okay, so that's our initial wallet. It's the thing that we'll start with. And again, we'll unfold from that initial wallet, which will produce a new transaction, which gets inserted into our wallet, which we then um, read from again. And so that's this next step down here that we need to implement. Okay, so we have a wallet that has some spendable box IDs in it, and we need to create a transaction that spends at least one of those spendable box IDs. Okay. Just to keep it simple, my plan here, I'm just going to pick a random one from the spendable box IDs, just one, and I'm going to spend it. So say like that's going to keep it simple, but I'm looking at my cheat sheet. That's makes it a little bit more complicated. It'll be fine. We'll be fine. Okay. So at the end of our for comprehension, again, we're returning a tuple. So I'll yield a transaction, which we haven't defined yet, and then a new wallet, which again we haven't defined yet. Yeah, righty. Step one, we need to pick which box we want to spend from our wallet. So for now, I'll just underscore. I'm going to rename that in a second. So first step, I need to shuffle our spendable box IDs. It's not entirely necessary, but whatever. I'm going to do it anyway. I'm going to do it using the cat's effect random implementation. So we'll do random from cat's effect f dot shuffle list. I'm going to pass in wallet dot spendable box IDs dot to list. And then out comes something that is shuffled. And I don't have random. So we'll go ahead and include that. Okay, now we have it. So, okay, so now we need to change what I'm extracting here. So I only care about the first item of this list. Again, like the output of this is a list. So I'm just going to extract the first element. And I'm going to ignore the rest. And in particular, this is a tuple of box ID and box. So this is going to be input box ID and input box. And so just using the unapply of tuple to extract those things. And again, this is a box ID, this is a box. And I don't care about the rest. Okay, so that's what we're going to spend. Next, let's extract the proposition from the box. So input proposition, or I shouldn't say extract it from the box because we're going to extract it from our wallet. So we know about some propositions. In particular, we're interested in the proposition associated with the inputs evidence. So input box dot evidence. Evidence. So that's the proposition that we care about. We're going to assume that we have it, and it's just going to crash if it doesn't. I'm not going to deal with the problems for now. This is just a little utility. We can improve it later. Okay, so that's the proposition. Next step is well, here. So why am I defining all this? Our ultimate goal is to create a transaction. So let me work from the bottom up actually. So transaction is going to be, well, in order to create a transaction, I need an unproven transaction that I attach proofs to. So let's assume that I have an unproven transaction dot prove. And let me define that up here. Unproven. Okay, so now I can call dot prove. And again, I'm just going to shorthand some syntax on here. This prove method, which I don't know why it's interesting. Okay. So this is another just like type class method that allows you to take an unproven transaction and it'll step through each of the propositions on each of the inputs of that unproven transaction and allow you to provide a proof for it. So it just this dot prove expects a function from proposition to proof. Because it's only got the one proposition that we care about for now, and because we're cheating a little bit, this is going to have to change in the future, but this will work for now. Um, we're just going to pattern match on just the height lock 0 proposition, and then we'll just attach a height lock proof. Doesn't require anything. Then I'm not even going to define. I could just keep the warning happy. Obviously bad practice, don't do this, but we're just doing a little helper utility for now, so it's okay. Okay, so this is our transaction. This is now like an actual transaction, so that's happy. And we need to also return a new wallet. So new wallet equals, and we need to take our old wallet and do a couple things. First thing, we need to update our spendable box IDs by removing the box IDs that we just spent. So moved input box ID. And then we need to add the box ID that we just created. So to do that, it'll be this gets a little bit fun because like all of the outputs that we are about to define, they're going to be multiple outputs, I guess. So I need to do a couple things in here. Instead of using updated, I'm actually going to add some items on here. So transaction.outputs.map with index, put index. Okay, in here we're going to do, okay, so we need to return some more tuples of this. So we need to construct, like for each of these outputs, we need to turn it into a tuple. So box.id, and then we'll pass in transaction.id, and then index.toShort. So that's the first part of the tuple, that's the box ID, and then the actual box is going to be output.address.spending address typed evidence, and then the value is going to be output.value. Okay, so that removes the box IDs that we just spent and then adds the box IDs that we just created. This is a chain, so I need to turn this into something that the Scala collection library understands. Okay, so that's our new spendable box IDs. The other thing that we need to do is update our propositions. So our new propositions is going to be yeah, I guess I'm going to do this anyway. This isn't going to change because we're just going to reuse the same height lock proposition over and over for each of the transactions that we create. But for the sake of being thorough, I'm also my cheat sheet. I removed propositions that we just consumed, but I'm not going to do that because we may still need those. So I'll keep them in there. Instead, I'm just going to add in any new propositions that we just created. So I'll pass in we're going to use our height lock proposition on the outputs. So the typed sorry, what am I doing? Yeah, and then the height lock proposition. That's our new wallet. And again, I'm working backwards from here. We haven't done like the actual magic yet, but we know that we need a new wallet, and we know that we need a transaction. And in order to do a transaction, we need an unproven transaction. So what goes into an unproven transaction? Let me just pop that up over here. Gonna drink some more water. Okay. So an unproven transaction. We need to specify the inputs of it. So this indicates the previous outputs that we want to spend. So the ones that we want to spend is just going to be a single input. So what am I doing? Chain of let's define our unproven. Well, yeah, no, that'll be fine. Transaction dot unproven dot input. So what does this thing need? It needs a box ID, a proposition, and a box value. So we can do that real quick. Our input box ID goes in here. Our proposition is our input proposition. Then our value is our input box dot value. Okay. So that's the input that we're going to spend. And again, I haven't attached so that's the difference between an unproven input and a proven input is this proven input has a proof. So I haven't provided that here. That technically gets provided here. Okay, so those are the unproven inputs that we want to spend. Next thing, we need to indicate our outputs that we want to create. So let's we're going to do that up here actually. So we have one input, and then for the sake of this little utility, we're going to split that into two outputs. So our like set of UTXOs is going to just grow and grow and grow and grow, like massively. Which is different from the other utility that I currently have, which it just creates a linear chain of one transaction spends the previous, and it just does that, etc. So this is going to create, like, I don't know, a bigger tree, hopefully. So to do that, we need two outputs. So output 0 is going to be transaction dot output. And the reason I'm doing output 0 and output 1 like this is just because I'm going to do some division and I don't want to lose polys. So I'll get to that in a second. Anyway, a transaction output, what does that need? Needs a full address, a value, and then a flag indicating if it's being minted. Don't worry about that for now. We're not dealing with anything that would involve minting. We're just going to be dealing with polys at the moment. Okay, so the first step is we need a full address. A full address includes a spending address and a staking address. For now, we're just not going to use anything special for the staking address, but I am going to create a little helper function that allows us to generate that full address using a spending address. So make a private. This one I'm going to have simple full address, takes in a spending address, and it returns a full address. Implementation, oops, it's going to be network prefix, just use 0, needs the spending address that was provided, and then the next one is a staking address, to use a non-staking. Finally is the binding commitment. I'm just going to stub in a bunch of zeros. So knowledge.add 25519, sized strict unsafe bytes.fill. These proofs are 64 bytes long, so we're going to fill them with 64 bytes of zeroness. Need some imports here. Cool. That's just a little helper method to turn a spending address into a full address. An actual wallet would need to do some more complicated things, at least in the future. For now, it's fine though. Okay, so now we have our helper method. So we're going to call it, so simple full address. Spending address is going to be, it's just the height log 0 address, I think. This one? Yep. Okay, so the value of this is where things are going to get fun. I'm going to actually compute that up here in another field. So quantity output 0 is going to be, okay, so I'm going to assume that our input box has a poly value like technically it could be arbits or assets or something else, but I'm going to do something bad. Input box.value as instance of box.values.poly. Don't ever do this in your code. I'm a professional. That's why I'm allowed to do it. Something. I don't know. It's in my title that I'm a professional. I question that. Okay, anyway. We're going to split our input box value. We're going to assume that it's polys. We're going to split it into two. Need a quantity dot data. Sorry, there we go. Okay, so now we have our new quantity. So our value for our output 0 is going to be box.values.poly quantity output 0. And then finally minting equals false. Again, don't worry about that for now. So that's our first sized dot max unsafe. And that work. There we go. Okay. So that's our output 0. Now let's define our second output. So output 1, it's going to look similar. In fact, it's going to look so similar that I'm going to copy paste. I'm going to change our value here to be, oh, is this why I did it in my cheat sheet? I'm just going to move this. Okay, so polybox value. Okay. So now our output 1 is going to have a quantity of polybox value dot quantity data minus output or quantity of output 0, and that's just so that we avoid potentially losing out on a poly. Like if we divide an odd number in 2. Yeah. We don't want to office space this where we have a rounding error. That would be really exciting. That was a great movie. Okay, anyway, our outputs is now a chain of output 0 and output 1. Okay. So we've defined our inputs and our outputs. Those are the important parts here. There are a couple other less important parts that well, yeah, I guess. Third part that we need is a schedule. In order to construct a schedule, we need a timestamp. I'm going to be fancy with the whole cat's effect thing and use the real-time instant. So our timestamp is going to be, this one's going to come from, I think it's from temporal. Async combines temporal and sync together, I believe. So async real-time instant. Yeah, I think I need to update this. Yeah. So this is going to be the timestamp of our transaction, and our schedule is going to be a schedule timestamp. Now we need to define some boundaries. So the minimum slot that we are allowing this transaction to be included is going to be 0. Maximum slot, I'm just going to say long.max value. I'm going to impose boundaries on this. This needs to be 2 epoch milli. So that's our schedule, and then final field is just data. For now, I'm not going to include it. We will need it for our, like the actual utility eventually, but for now I won't. Okay, so our unproven transaction, start filling these in. So outputs and then schedule and then none. Unproven transaction. Need to update that. Come on. Figure it out. Oh, it can't figure it out. Need to do one more thing. Need randomness. So we need an implicit. I'm going to use another SBT plugin that I don't remember the name of that allows you to embed an implicit into a for comprehension. But an implicit random This is going to be random. Just use the Java secure random. So we have that in scope. Cool. How long have I been going for? A little over an hour. This is about where I made it on the cheat sheet anyway. So, okay. So let me back up and explain some things in here, and I'll go through like from the beginning this time. Okay, so we want to come up with the next transaction using this wallet that was provided. So step one, we need to select which inputs or like which UTXOs we want to spend. And so that box ID is going to be used as the input of our transaction that we will consume. Next step is we need to come up with the values that we want to produce in our transaction. So I'm taking the input UTXO and I'm splitting its value into two and producing two new UTXOs that can be spent later. Next up, I'm coming up with the schedule to associate with that transaction. Next, I'm creating the unproven version of that transaction. And then next, we create the actual transaction by signing the unproven transaction or proving it. Then finally, we update the wallet that was provided by removing the transaction or the UTXO that we're spending and introducing the UTXO that we're creating, and also updating the propositions that we know about. Okay, so because this returns a new wallet that has a new set of UTXOs, the next time this method gets called, it's going to pick a different one to spend. It'll go and create a new transaction. It'll create a new wallet with a new set of UTXOs, and then it'll plug back into here, where it just repeats that cycle over and over again. And it does that using this unfold eval. So this will run forever and ever, or for as long as a consumer wants transactions. Okay. Pop back into our unit test and update this real quick. I'm going to need my cheat sheet again because I needed to create a seed transaction, and I don't feel like doing that again. Okay, so step one is create a seed transaction. Transaction. It's just going to, it's not going to have any inputs. This is our Big Bang transaction. So it's going to need to import these. So what are you analyzing, IntelliJ? Whatever, it'll figure it out eventually. Okay, so those are the inputs. There are none. The outputs, it's just going to have a single output that we can spend. And I'm going to just use that little helper method for the full address that I defined. So fs2 dot. What is going on? Like what? Do you need help, IntelliJ? Like, why are you making me do all this? If I wanted to figure things out myself, I'd use just a basic text editor. You know what? For the sake of time, I'm going to copy paste from my cheat sheet while IntelliJ figures it out. And then I'll explain what I just copy pasted. So I updated our unit test that previously expected an empty stream of transactions. So now it produces a stream of transactions. I'm creating our first transaction for the Big Bang. It's got 0 inputs, but it has one output of quantity 1 million polys. The spending address is just, the height log 0 address. And our transaction schedule says that it can only be included in the Big Bang block. Okay, next I update the call to the make method. I pass in that seed transaction, and that allows it to create the initial wallet. Next, I call that generate transactions to produce the stream. but again, it hasn't produced any values yet. So now I say I want to take the first 5 values from that stream, and then I force it into a list. And now I'm just checking that the length is 5. Really, I just had that in there so that I could pause and breakpoint. Wait, why doesn't it like this? Oh, it's because I hadn't finished compiling it. Okay, or copy pasting. Let's try that again. Did not like it. It's because I used a different name. This is what I get for copy pasting. You should never ever copy paste, folks, unless it's for a paper in high school and it's due tomorrow. What did I do? Oh, this one. Oops, my bad. You're right, IntelliJ. Gotta fix all of these. Of course, if you would analyze faster, you could show me the red squigglies and then what? What? I don't know what it wants from me now. I am confused. IntelliJ, come on. Let's get it together. You know, I'm gonna restart this real quick, sorry. Man, hurry up and load. Still analyzing. An IDE error occurred. I think this is because I decided to update my Scala plugin right before the broadcast, so that was a fantastic idea. Whatever, I'll just keep pressing this button until it works. That always fixes it, right? Also, if anyone has any questions or comments, feel free to leave them in the chat. Be happy to take a look. Also, if you're watching from YouTube, feel free to hit that the little subscribe button. Hit the notification bell. You'll get yelled at anytime we go live. It'll be fun. Okie dokie, it is still not working properly. It's because my package name is incorrect. I also changed that. My bad, IntelliJ, you're right again. Okay. Again, somewhere. Height log 0 address. It's spending address now. Okay. Almost got it running. Error running. This is horrible. I'm so annoyed right now. Like, why can't IntelliJ do this? I think I'm gonna have to. Oh, geez, which one? This one will do. Wow, everything's breaking now. Like nothing's clicking here. Okay, this is going real well. So I was hoping to just like run this stupid unit test and then close out the broadcast, but IntelliJ doesn't want me to do that. Okay, hopefully that cleaned it out. Let me restart SPT one more time. IntelliJ, I'm gonna need you to get it together here. It's still analyzing. I don't know what the deal is. Okay, please work. Wow, IntelliJ cannot even find it. What the heck? Oh, good. More IDE errors. Yep, don't know what's wrong there. Yeah, IntelliJ still can't analyze it. I don't think this is gonna work. I don't know. Oh, wait. Oh! It's because this is incorrect. Okay, but it's still not. Oh. Okay. Alright, so it passed. Alright. Making progress. I don't think that I can add breakpoints though because it's still analyzing. So, oh. Here we go. Yeah, add one there. I just wanted to look at the transactions real quick before we wrap up for today. Okay. So yeah, we can see that. So going in order, this would spend the first transaction. Yeah, with the million. And then it split it up into 500,000 and 500,000. And then the next transaction specified, I don't know which one, but one of them, spend 500,000. And it created two new outputs with 250,000 each. And so it just did that from there. And eventually 125,000. Okay. So yeah, it's splitting them up, breaking them down. Let's I don't know, just for fun. I don't know why I removed the breakpoint. 50. $3,906. Okay. Yep, 3907. And so yeah, we didn't office space it because this was 7813. Those two should hopefully add together. Okay. Again, why did I remove the breakpoint? Let me run it one more time. We're gonna. I have no idea how long this is gonna take. Let's find out. 50,000. Don't know if this will even work. I didn't test it. Yeah, I mean, it's got to unfold one after. Well, I don't know. Maybe it could do some things in parallel. It did fail though. So what happened? Longer than 30 seconds, of course. Okay, so I'm gonna have to figure something out to make this better. Because I don't think that this is gonna. Like, we want to test more than 1,600 transactions per second. I think we want to go faster. Then again, that's just generating from one node, but all the other nodes need to be able to process each of these. So yeah, I don't know. Anyway, that's what I got. It's almost an hour and a half. I'm tired. Talking's hard. I don't know how people do this all the time. It's so difficult. Anyway, I'm happy that I got to implement something. Happy that I got to jump on and do an engineering broadcast again. It's been a little bit, so yeah, it was good. Anyway, again, this is in preparation for tomorrow's broadcast, where we want to push the limits of a Raspberry Pi running a blockchain node. We want to see how hard or like how many transactions it can handle right now, and then we're going to be making improvements over the coming months. So we want to see how it does, later. Mostly, we just want to mess with the Raspberry Pi. It'll be fun. So yeah, that'll be tomorrow at 4 p.m. Central. Definitely, feel free to tune in. We'll be using this utility, hopefully, and we'll break a Raspberry Pi. Okay, so as always, thank you for watching. You can see that QR code that'll take you to our link tree. Otherwise, you can go to Linktree. That's linktr.ee/topple_protocol. That'll give you a link to all of our our socials and banners and everything, YouTube, Twitch, Twitter, all that kind of fun stuff. And subscribe to all those platforms. Thanks for tuning in, everyone. Hope to see you all tomorrow. So yeah, take care.